Hello everyone. In today's video, we will be discussing another topic, that is Doppler effect. In this, we will see how the Doppler effect works in sound and how it works differently in light. So let's get started. Before starting the video, I would like to share that the physics handouts are available. You can buy it from the link given in the description box. So let's get started. So let's first define what is Doppler effect. Everyone knows, so let's just define it first. So it's an apparent change in the frequency of waves due to relative motion between source and observer. Because of the relative motion, there's a change in the frequency. So let's first see Doppler effect in sound. We know when the source of sound approaches us, the pitch. What is pitch? Pitch is the measure of sound frequency. That means higher the frequency, higher will be the pitch. As the source of sound approaches us, the pitch increases. That means the frequency of the wave increases. So our observed frequency mu will be mu naught times, that is the original frequency. This is the original frequency of sound. We just have to multiply this original frequency with a fraction which is given by, this is Vs plus V naught Vs minus capital V, where Vs is a speed of sound, V naught is the speed of observer, this capital V is speed of source. So this is a fraction. We know as the source approaches us, the frequency will increase. So this fraction should be more than 1. The speed of sound gets added to the speed of observer in the denominator. So we have to subtract the speed of source from the speed of sound. So this fraction will be greater than 1. From seeing this expression, we can say the frequency of the sound increases as the source approaches the observer. So now let's discuss the sign convention. So the sign convention we will be using will be positive for towards motion, negative for away motion. We know the Doppler effect in sound varies with the relative motion between source and the observer, but this appears to violate the principle of relativity. So why I'm saying that, let's see. Because sound waves occur only in a material medium such as in air or water, and this medium is itself a frame of reference with respect to which motions of source and observer are measurable. But that's not the case for light. So let's see the Doppler effect in light. So the Doppler effect in light, we all know light need no medium. So there's only relative motion of source and observer. So let's consider a light source that emits light pulse mu naught times per second. So it's basically a light frequency. So let's start with our first case in which observer is moving perpendicular to the direction of light. If this is a source, light source, this O is an observer, the light direction is this, observer direction is perpendicular. This is known as transverse Doppler effect. So it's a transverse Doppler effect where there is a transverse relative movement between source and the observer. So the proper time between successive light pulses will be 1 over mu naught. In the observer frame of reference, the time elapsed would be the proper time over the root of 1 over v square by c square, where v is the speed of the observer. So the transverse observed frequency can be written as is equal to 1 over t, which is equal to 1 over tau naught, then the square root of 1 minus v square by c square. So that would be mu naught 1 minus v square by c square. So this is an expression for the observed frequency in transverse Doppler effect. Let's see the case 2, where observer is moving away from the light source. So if it is a light source and this is observer here, the observer is moving away from the light source. So it's a longitudinal Doppler effect. So longitudinal Doppler effect consists of two cases, away case and towards case. We are dealing with away case, and then the third case will be towards case. So these two would be the longitudinal Doppler effect. Direction of light is in line with the direction of observer. Observer travels the distance vt away from the source between the two successive light pulses. The second light pulse takes Vt over c longer to reach him than the previous one. So the total time taken between the arrival of successive waves would be t plus Vt by c. We can take t common. This is 1 plus v over c, and this is can be written as t naught over 1 minus v square by c square, and this is 1 plus v over c. So let's move to the next page. So the total time between the arrival t naught root of 1 plus v by c over 1 minus v by c. So we can now get the expression for observed frequency. You just have to reverse it. So this would be v naught 1 minus v over c. This is 1 plus v by c. This is the away case. Now let's do the last case, that is case number 3, where observer is moving towards the light source. If this is a source, this is observer, then the direction would be like this, moving towards each other. So I'm fast forwarding it. So the total time would be e minus vt by c. Observer moves the distance vt towards the source, so we have to subtract the time vt by c. So we can do the mathematics thing now. So after doing this, we get t naught 1 over minus v square by c square 1 minus v by c. So this is the time. So we can find the observed frequency, which is equal to mu naught 1 plus v by c 1 minus v by c. So this is our observed frequency for the towards case. We have seen all the three cases. So this is a question. You can try this and you can write the answer in the comment box. So this is it for this video. If you have any doubts related to this topic, you can write me in the comment box. And if you like this video, please like, share and subscribe to my channel, and thank you for watching this video.